Alright, hey guys, what's going on? So today we are going to be talking about Papa Riemann, the Riemann Curvature Tensor. Right, so the Riemann Curvature Tensor is usually where you stop at a general relativity course or tensor calculus course, but we're going to go beyond the Riemann Curvature Tensor, but we're going to spend a couple of videos on the Riemann Curvature Tensor because it's a super important tensor and we're going to really get familiarize ourselves with this tensor. But anyways, again, make sure to hit that like and subscribe button. Make sure to hit up my Patreon page as well if this is the kind of content that you're interested in. Now let's get straight into the topic. Alright, so we're talking about the Riemann Curvature Tensor today. So at this point we've established a torsion tensor. Now we move on to talking about curvature. Alright, so curvature and torsion are intrinsic properties of a manifold or a path. And so we've covered this before. We can think of curvature as a force that a particle feels as it's traveling along some path. And the torsion is something that the particle experiences as well. These are two things, two intrinsic properties of a curve that a particle feels or that something feels as it's traversing that path. And we've come to understand the torsion tensor. Now let's go ahead and start looking at the curvature tensor. So sort of from a bird's eye view here, Newton's ansatz was that curvature equals force, right? So if there's a curve in some geodesic, or if there's a curve, geodesics by definition are actually not curved, they're straight, but we'll get into that. That's something that we'll get into a little bit later when we talk more about geodesics. But the idea here is that curvature equals force, so the Riemann curvature tensor is going to be related to some sort of force, okay? Sort of in the physical world. It's going to manifest itself in that way. The Riemann curvature tensor is a rank 1-3 tensor or a rank 4 overall tensor. And like we said, it's going to be associated with some force that a particle feels as it's traversing a path. Now, you can go into Wikipedia, very reliable source, JK. The Wikipedia says that there's actually two parts to the Riemann curvature tensor. One is a part in which the object experiences a change in shape as it's traversing a path. And the change in shape as it's traversing a path, well, this is going to be the traceless part of the Riemann curvature tensor. And the traceless part of the Riemann curvature tensor is going to be the Weyl curvature tensor, or just the Weyl tensor. We'll get into this guy also. Volume changes correspond to the trace part of the Riemann curvature tensor. So we'll be able to understand what exactly is meant by trace and traceless part of a tensor, just like trace and traceless parts of a matrix. But that's going to be represented by the Ricci tensor. And then we'll get into more tensors as we go forward in this playlist. So let's actually compute the Riemann curvature tensor. We want to compute what it is. We want to compute its components. So we're going to start off by finding the covariant derivative of some vector on a manifold. The way we do that is we take a look here. We have some vector in green here. Sometimes, suppose that vector looks like this, and we want to go in the direction, in say this direction that's represented in this direction on the manifold. These are representation vectors, or these vectors are representations of directions we go and vectors within a certain point on that manifold. And I've brought this picture up a number of times now, but we're going to go along this direction. So let's go ahead and do that. We have the covariant derivative of a vector in the one direction, right? So this is the one direction. This is going to be the two direction, and we're going to calculate the two direction later. But let's do this now. So, okay, so we have this right here, right? So the covariant derivative is defined in this way, as we've seen before, and this is the vector. All right, moving over the tensor product, which we can do. This is all linear. All right, so this is all linear, that means we can do this. We then move on to expanding this guy out. So this is the covariant derivative, and then this guy here is encapsulated in the affine connection. All right. From the affine connection, from this here, we can get, use our dummy indices to extrapolate this covector out. All right, so this is our basis vector. And then we can move E1 out to this end over here. So we get something that looks like this. This is, again, just the covariant derivative. It's a rank 1 tensor, and we got it from a rank 1 0 tensor. So this again was a tensor. We have shown that this was a tensor. We've shown that this was a tensor, and we get this guy right here. Okay, so now we take the covariant derivative in a new direction. So we moved in this direction. Now let's move in the 2 direction. Okay. The 2 direction, this can be thought of as dx1, and then the blue guy dx2. Those guys are thought of again as vectors. This is a basis, and so that's why we can do this, right, this step right here. Okay, so we're moving in the 1 direction, then we move in the 2 direction. Okay, so now we get this, and we're doing the same procedure, but it's a little bit more complicated because now we're taking derivative of a covariant derivative, but this isn't too bad, right? So what we can do is we can expand this guy out, right? This guy out like this, so we get this term, we get this term, right? So this is the derivative of the basis vector of this 1, and then the derivative of E alpha. All right. Then we get this. This here, we realize that the derivative of the basis with respect to the coordinate is an affine connection. And the same thing right here. Okay. The reason this is not negative is because here in an earlier video we found that the affine connection for covectors was just the negative of that for the vectors. All right, and so we get, so from here we get, so this thing is staying the same, this thing is staying the same, changing some dummy indices over here. All right, so when we change the dummy indices, we see that E alpha, and E alpha. All right, so that we're essentially taking the basis vectors out and we get something that looks like this. So this is the component of, this is a component of that double derivative, of that double covariant derivative. Okay, now we can expand this guy out to get this, right? These are all just covariant derivatives, right? So again, you could pause the video if you want to take a look at this, but this is what we get. Here's our basis vectors. All right, so this part is a little bit long. So what we actually calculated was this. So all of this right here, all this right here is that we're just foiling things out now. We're foil things out like this. All right, when we do that, we get this term, right? So that's this term. And then this term here is the second term. And what you'll see is I'm actually taking out that V. There should be a V mu right here, right? There should be a V mu and a V mu. because then that shows up right here. All right, and then it looks like there might have been, oh, okay, I see what I'm doing here. So we need that V mu, and then, so that's what we get for here, right? So we're foiling out everything. We get this really, really long, boring thing. And what we're going to do now is we're going to, wherever we see 1, we're going to swap for 2, and wherever we see 2, we're going to swap for 1. So it's the same expression, right? But we swap out 2, 1, 1, 2, 2, 1, 1, 2, and we're just doing that for the whole thing. All right, and I hope I got everything right in here, but you can pause the video at certain points here just to double check my work. But then the point here is that now we want to subtract these two things. And when we do that, we're going to get something that looks like this. A lot of things are going to cancel. Right? So let's see here. So these guys are going to cancel, right? And then we get, so these terms are recovered. These terms are recovered. And then we need, then the two derivative terms, these terms are recovered. And these terms go away. The reason these terms go away is because they're the same, right? If we assume torsion freeness, these things will cancel. If we assume torsion freeness, these things will cancel. So this is torsion free, right? So we want to keep that in mind. But now, so now we're interested in reversing this path. So this is what's meant by sort of closing the loop, if you will. So we went this way, and then we went this way, and then we swapped. We went 1. So we went 1 and 2. Here, I'll go back really quick. We went 1 and then 2. And then we'd take the derivative of 2 and then 1. So we went 1 and then 2, then take the derivative of 2 and 1, and we get this closed loop. Okay? And what I'm realizing here is that I don't need this. So I don't need this right here. That's just a copy of what was in the earlier video. What we end up with was this. Okay, this was just the same equation down here. Okay, and then we changed some dummy indices around, right? So I'm just highlighting mu's, and gammas, right? And we're changing some dummy indices within here, and this is what we get for our Riemann curvature tensor. This is the equation for the components on the Riemann curvature tensor, and so this is how we define the tensor. In flat space, these guys are going to be 0, right? If these guys are going to be 0, the derivative of 0, 0, derivative is 0, 0. These guys are going to go to 0 as well. So in flat space, the curvature is 0. And the consequence of R not being 0 means that there's a difference in this closed loop. So if we come back to this closed loop, in one case we went this way, and then this way, and then we took the difference of that in going that way, and then this way. So that's what I'm depicting here. We went 1, and then 2, and then 2, and then 1, and we can see when we parallel transport, we get actually two vectors that are different in that final position, or in that final state. This is also associated with parallel transporting, say, along a sphere or some sort of geometric non-curved object. So what this is imagine you're looking out in this direction, okay, and then you start traveling down this way. You don't move. I like to think of this as you're not moving your head as you travel, right? So you're always looking in front of you. So as you travel down this way, you're still looking in front of you, still looking in front of you, still looking in front of you. Right? So then you don't move your body or anything. You keep on walking across here. So you're kind of like walking sideways, if you will. And then you walk backwards. And you're not changing the orientation or position of your head as you're doing this. That's sort of what I like to think of as parallel transport. But what we end up with is a discrepancy in the end state vector and the initial state vector. Or not state, right? We're not talking quantum mechanics. But these are vectors that are different in orientation from each other at the same point upon parallel transporting. And the Riemann curvature tensor tells us it tells us to what degree these things are not the same. Okay? It tells us to what degree these two guys are not the same because, again, we calculated the difference between this and this. Okay? And so that's one way to think of curvature. One way to think of curvature is that when you parallel transport a vector around a curve and it does the two vectors at the initial and final position, which is the same place, if they're not the same, then the object is curved. So you can imagine doing this on a flat plane. Suppose you're on a flat plane and you're parallel transporting. Well, if you parallel transport, say you're looking this way, you look this way, look this way, you keep on looking this way. Okay, keep on looking this way, and you get back to the initial point. These two guys are the same, and so the thing's flat. We have a case of flatness. Okay, in the case of curvature, this is not the case. This is not. These two vectors are going to be different from each other. Okay. So however, I gave the coordinate free definition of the Riemann curvature tensor in earlier videos, which was this, and so we need to understand this as well. Since I'm pushing on 20 minutes, though, I don't want these videos to go on for too long, and so in the next video, we're going to cover this. The next video is actually going to be quite long because I really want to push through the Riemann curvature tensor, and I really want to get to some pretty exciting stuff in tensor calculus. But with that being said, I hope you guys like this kind of content. Make sure to hit that like and subscribe button, and I'll see you guys in the next one.